The radiative energy balance of the Earth is complicated farther by the interactions with the fluid environments of the atmosphere and ocean. Remember what I said in the last lecture. The global temperature of the Earth is a balance between heat absorbed by radiation and heat lost by radiation. When this balance is changed, the Earth comes to thermal equilibrium at a different temperature. The relative opacity of the atmosphere to radiation of different wavelengths complicates this simple relationship considerably. The presence or absence of water vapor, for example, affects the relative absorption of radiant energy by either the atmosphere or the surface. At the temperatures at which the Earth radiates in the far infrared range, the presence of carbon dioxide has a noticeable but small effect on how heat is dissipated from the Earth to the cold night sky. Complicating the Earth's energy balance still farther is an interaction with fluid motions of the atmosphere and oceans. Here is the Earth, with ocean in blue and land in brown, and the Sun some distance away. The Earth spins on its axis, which in this cartoon I've oriented vertically. There are several latitudes on Earth that serve as convenient markers. At 0 degrees latitude, of course, is the equator. At plus or minus 23.5 degrees latitude are the two tropics, the Tropic of Cancer in the northern hemisphere and the Tropic of Capricorn in the southern hemisphere. At plus or minus 23.5 degrees from the poles are the polar circles, the Arctic Circle in the north and the Antarctic Circle in the south. The intensity of solar radiation streaming into the Earth depends upon the latitude. At the equatorial latitudes, solar energy coming in is direct and the irradiance is high. At higher latitudes, solar energy streams into the Earth at an oblique angle, and this means that the irradiance is lower. This differential in heating sets up several so-called atmospheric circulation cells that are aligned with our designated latitudes. Around the equatorial regions, air is warm and humid and therefore buoyant. Air at the equator is lofted up into the atmosphere, producing a circulation cell known as a Hadley cell, one to the north and one to the south of the equator. Between the tropical latitudes and the temperate latitudes, there's another set of circulation cells known as Ferrel cells. Again, there's one in the north and one in the south. Take a close look at these patterns of circulation. At the equator, the air in both Hadley cells rises. This lofted air is replaced by surface air streaming in from the more tropical latitudes. At the tropics, the air flows between the Hadley cells and Ferrel cells are coupled into a net downward motion. The same consideration applies to latitudes above the polar circles. There is a north polar cell and a south polar cell. At the polar circles, the air in the polar cells and the air in the adjacent Ferrel cell both rise. At the poles, meanwhile, air descends from high in the atmosphere down to the surface. These patterns of circulation have significant effects for the local properties of the atmosphere. At the junction between the north and south Hadley cells, for example, the air is warm and it is also humid, both of which reduce the density of air. This reduced density is what makes air at the equatorial latitudes buoyant. At this latitude, low barometric pressure prevails. This is why the air rises at the equator. It is also why there is typically considerable rainfall at the junction between the north and south Hadley cells. At the junction between the Hadley cells and Ferrel cells, in contrast, dry air streams downward and encounters surfaces that are quite dry. Barometric pressures here are typically high. Going further poleward in latitude, at the junction between the Ferrel cells and the polar cells, air is humid and cool, again with prevailing low barometric pressure. At the polar cells, high barometric pressure again prevails with dry and cold and therefore dense air descending towards the ground. There are also circulation cells contained within the oceans. We're going to show these in considerably simplified form here. In general, waters of the equatorial regions are dense, in part because they have evaporated quite a bit more water so that their salinity is higher. These dense waters sink towards the ocean floor and are pushed towards the polar regions where the water is lighter, in part because the inputs of fresh waters from continental rivers are higher there. The overall result is a conveyor of heat from the equatorial and tropical latitudes up towards the polar latitudes, warming the polar latitudes more than they otherwise would be. All this is looking more like a lecture from the fluids module, isn't it? What's it doing here in wave phenomena? Good question, and here's the answer. We're looking really to understand the Earth's global energy balance. And this is not just a matter of radiative heat inputs and radiative heat outputs. It's also a matter of where the heat goes in between. Global patterns of atmospheric and oceanic circulation also profoundly affect the Earth's energy balance because they redistribute heat from the equatorial and tropical regions of the Earth up to the polar regions. These different areas differ considerably in atmospheric composition, particularly with respect to water vapor, which, as we have seen, is the most important greenhouse gas. And note well that the poles and tropics are typically dry, whereas the equator and temperate zones are typically humid. Let's simplify our diagram of the half-Earth a bit. The effect of incoming solar energy differs between the different latitudinal zones. Sunlight streaming into the relatively humid equatorial regions and the temperate regions near the polar circles disproportionately warms the atmosphere. Why? Because these latitudes are rich in water vapor, which absorbs solar radiation in the visible and near-infrared spectral bands. Around the arid tropical latitudes, in contrast, the atmosphere is relatively transparent to these long-wave and infrared bands, and consequently surface warming there is quite substantial. Radiative cooling at night is also quite strong. There's some redistribution of atmospheric heat from the equatorial latitudes to this region, but air has a fairly low thermal capacity, and so the redistribution of heat by atmospheric circulation to these latitudes is relatively weak. However, remember that the thermal capacity of water is about 3 orders of magnitude larger than air's. This means that the oceanic heat conveyors transport a considerably larger amount of heat from the equatorial and tropical latitudes up to the polar latitudes. There, the air is very dry and very cold and is not strongly warmed by solar radiation. This means that at these latitudes there is a considerable loss of heat by a long-wave infrared radiation from the Earth to the cold night sky. CO2 has an effect here, but it is very weak. So the overall pattern of heat redistribution by the ocean conveyors is from equatorial and tropical latitudes up to the polar latitudes. There, heat streams out via long-wave infrared radiation through the cold and dry atmosphere. At these wavelengths, the atmosphere is mostly transparent, even with modest amounts of carbon dioxide. All of this makes for a very complicated climate system. We can't really go into too much depth here, but we can illustrate the complexity of the problem by looking at reconstructed global temperatures through the Holocene, beginning about 1.2 million years ago up to the present. We plot here the relationship as a so-called temperature anomaly. This is basically the difference between past global temperature and the average global temperature during the pre-industrial period, when the effects of anthropogenic CO2 were presumably nil. These scientists were able to estimate average global temperatures over the last 800,000 years. And here is the trace of what these reconstructed temperatures look like. Notice how temperatures are generally cooler than the pre-industrial average. Is this due to higher levels of CO2 in the atmosphere today? That's unlikely. The climate of the Holocene involves repeated periods of strong glaciation or ice ages, indicated by strong dips of global temperature down to as much as 6 degrees below the pre-industrial average. Interspersed with these glacial periods are so-called interglacial periods, marked by temperatures that are warmer than the pre-industrial average. This is probably why average temperatures through the Holocene are generally cooler than the pre-industrial average. Presently, we're in the latest interglacial period, and we only began to emerge from the last ice age about 6,000 years ago. Global temperatures warmed during the interglacials, and that is why global temperatures have been on the rise lately. CO2 levels in the atmosphere have had little to do with it. But back to these Holocene temperatures, which swing abruptly back and forth between glacial cool periods and interglacial warm periods. What's driving these remarkable and seemingly abrupt changes of global temperature? One possibility is the variation of intensity of solar radiation. One can estimate the so-called solar forcing of global temperature from various astronomical measures, and we see that there is indeed quite a bit of historical variability in the intensity of solar radiation. This will certainly have an effect on the incoming stream of the Earth's radiant energy balance. This variation of solar radiation can be as much as plus or minus 25%. But the correlation between variation of solar forcing and variation of global temperature appears to be fairly weak. Peaks in solar forcing correspond only weakly to peaks in global temperature. What really affects the climate is the ability of the oceanic heat conveyors to distribute heat from the equatorial and tropical latitudes up to the polar latitudes. When there's a strong oceanic heat conveyor, that is, ocean currents are redistributing considerable amounts of heat poleward, this correlates with warmer temperatures in the polar latitudes and, as a consequence, interglacial periods. In contrast, when there's a weak oceanic heat conveyor, heat is retained in the tropical and temperate latitudes. These latitudes therefore tend to be warmer, and the polar latitudes tend to be colder. Glacier formation is therefore enhanced, producing an ice age. So, what can we conclude from all this? At this point, about the only thing we can conclude is that the energy balance of the Earth is extremely complex, and that no one can claim to understand it very well. Climate change, for example, is not a simple matter of increasing carbon dioxide concentrations in the atmosphere. We know that this has an effect on radiation heat loss from the Earth, but its effect on long-wave infrared radiation from the Earth is actually quite weak. When we talk about the other side of the radiation energy balance, that is the input of energy from the sun, the effect of carbon dioxide is negligible. On this side of the energy balance, it's water vapor that is by far the most important greenhouse gas. When we talk about the ways that the Earth actually balances its energy budget, patterns of oceanic circulation and the latitudinal redistribution of heat that goes along with it become far and away the most significant influence on global climate. The rub, of course, is that all of these complex patterns of heat distribution, radiation absorption, and radiation dissipation are coupled, and that is where the uncertainty lies.